Hi everyone, welcome back to our Learn Live session on learning machine learning. I'm back here with my good friend Jason. Hey Jason.
Hey Glenn, good to be back with you.
Excellent. We've got a lot of stuff to go through today. We're going to look at confusion matrices and data imbalances. It's going to be a lot of fun, a lot of interesting stuff. Um, a little bit less mathy, I think, than the last few weeks.
It's not terribly mathy, but I'll be honest with you. There's something about the topics today that have a hard time sticking in my own brain, at least in terms of matching the labels and labels is another bit of jargon, but in terms of matching the terminology to their concepts. The concepts are easy, but for some reason it's one that it's almost like memorization. It's like memorizing geography or something for me, that this word maps to this relatively simple equation. And because it's not sticky for me, it makes it seem harder than it is. That's me. Hopefully everyone else doesn't necessarily feel that way,
Yeah.
because the actual math parts are super easy. It just doesn't like to stick for me sometimes.
Yeah, so I'm the opposite. Maybe we'll talk about those bits that stick and the bits that don't as we get to them. But there's a lot to go through today. So for those of you who are just joining in, or maybe you'll be watching this later on one of the pre-recorded videos, Jason, do you want to introduce yourself to the world?
Yeah, hi, I'm Jason DeBoever. I'm a senior product manager here at Microsoft, working on our content side of things. And specifically, I work with AI and ML content, which is why you have me here today.
Good. And my name is Glenn. Glenn Stevens. If you've not met me before, if you have, great. If you haven't, that's okay too. I'm a senior content developer working on the Learn Live team, and I work across a huge range of content, really. But let's keep going. And and this is our penultimate episode, our second last one in the entire series, and we've been here for quite a long while. And for those of you that have been following along, it might seem a little bit friendly. But we're at the confusion matrix and data imbalances. This is number 8 of session 9. Next week is our last one, where we're looking at optimizing model performance with ROC and ORC. But we've learned a lot already. So if you haven't had the chance to go and see those first chunk of videos, I'd highly recommend that you go back. There's a lot of great content in there on learning regressions, learning how to work with data, and a range of other great presentations.
And while it's fun to just hang out with Glenn and I don't want to say to anyone, don't just hang out and just listen to us talk, because we're great. You will get a lot more out of today's session if you'd already attended some of those other sessions, for sure. But by all means, even if you didn't, stay here, hang out, let's talk.
Cool.
And today's session, by the way, comes from a Learn module, as do all of our sessions on Learn Live, of course. So there's a Learn module that maps to every single one of these episodes. And if you want to follow along at home, as I'm sure many of you do, or go through these exercises later, the demos, the exercises that we do, you all get to do them in an environment that we provide. It's free. The execution context, the CPU, the setup, it's all done for you. All you have to do is log into Microsoft Learn at the URL you see on your screen. As a matter of fact, take you right to this module, log in, and start working with the code, tweak the code, change the code, do what we do, then do something else. It's a really fantastic experience for learning.
Excellent. And you know what? Here's the things that we're actually going through today. So we're going to look at classification models. We've already covered classification models a little bit already. We're going to look at how we can actually use the confusion matrix to improve some of the classification models, because if we're using things like cost functions, we only get what's wrong, but not which particular types of classification errors are we getting. And we're going to look at performance issues from data imbalances. Anything I've missed out there, Jason?
We're going to look at some of those jargony terms that people toss around. They mean the same things as what you're talking about, but because it's the lingua franca of training models, we do need to at least be familiar with these terms, and then and have a vague idea of what they mean and what they're based off of. If you're like me and some of these words, this glossary just isn't sticky, that's okay. Once you're familiar, you'll have the ability to do that quick reference lookup. And I think that's the important thing, is having enough familiarity with some of these things that the lookup into the reference materials is quick, snappy, and easy. You don't necessarily always retain every detail.
Awesome. And I'm looking at the next slide. We actually are live and interactive. And we've got some people listening already. There's some hellos from Melbourne, Australia, which is like my neck of the woods, closer
fantastic.
to it
Excellent.
than where you are in Detroit. But if you're calling in from all over the globe, let us know. We've got someone from New Zealand as well. Amandeep, welcome.
Brilliant. They're all from your side of the universe. What's everybody doing up so early over there in your side of the universe is what I want to know. Over here, it's actually a decent hour. I'm sorry.
It's quite good.
What time is it there, Glenn?
Well, it's just on 7 a.m. for me. I think in Melbourne it would be 8 a.m. And in New Zealand, depending on where you are, it's probably around 9 or 10 a.m. The reasonable times.
Reasonable times for everyone except you.
Yeah.
5 p.m. here in Michigan. So let's see. All right, we've got plenty of folks all around. Oh, I didn't actually introduce our wonderful moderators. Sorry, I almost skipped that slide. Speaking of being live, we are live with a chat session, actually several chat sessions across lots of different platforms that we are broadcasting on, and our amazing moderators are there to help with your questions in real time. They'll even share some of those questions up to Glenn and I and let us take a crack at them. But no matter how many questions and how hard those questions are, we've got people who can answer them because they are experts, and we've got enough of them to cover all the questions you may have.
Excellent. Cool. Well, let's get into the content. I can actually see some more hello messages. Hi to Jim and Nadine. Jim's from Mountain View, California, and Nadine's from Montreal. Cool. Closer to your neck of the woods, Jason. That's wonderful.
Closer than you than they are to you at any rate. We've got Deepak from Berlin, so that's not close to either one of us. That's great. We've got the globe covered well, I think, and Virginia in London, also not terribly close to either one of us. The globe is well covered, I think. Welcome to everyone. Really glad to have you all here. All right, so today we covered this a little bit with the learning objectives, right? But the reality is we're going to be talking about how we can get into improving our classification models and really looking at what we think is wrong with them, actually. And this is sort of the data analysis part. So after we've trained some models, we want to go back and look at how they're performing and what we think we might need to be stressing in order to get them to work better. And we're going to look beyond just kind of the basic accuracy scores that are the first thing we start to think about when we're first evaluating a model. We're going to get a little deeper than that today. And as always, we've got a scenario we'll be playing with as we talk through these issues. So what can you tell me about this scenario today, Glenn?
Well, we're back on the mountain again. So we've had this scenario a few times where we're really detecting avalanches occurring. So in this case, we've got some hikers that are venturing out without logging in, and so we're not really sure if we have an avalanche, are there hikers on the mountain or not? And an amazing donor has donated a bunch of drones to actually go out and check out the landscape. Yeah, there's nice little quadricopters, but they've got cameras. They can't send video back. So what they're doing is essentially taking photos and trying to determine basically information like what color do they see, what's the movement, et cetera, and send that back to base. And then base is using that information to interpret what kind of object it likely is. So they don't have the great internet infrastructure they do to send live video, but they're working with what they have.
And even the human resources, if we have hundreds of cameras, perhaps we don't have people watching and staring at a screen for each camera at every time. So by having a machine learning model that can identify a likely problem, we can then say, oh, I see this one is something that might be a person in this area where there was an avalanche. Let's get some human eyeballs on that.
Yeah, exactly. And they certainly don't want to have to send people out if there's no hikers on the mountain. So if there is an avalanche, are there hikers on the mountain? That's the real question they want to answer, so they can go out and find people.
Yeah, and it's kind of the double-edged sword because if we have what we call that false positive, that is, we're saying there's a hiker there, but there's not, we're wasting rescue resources. But if there's a false negative, it's even worse. We're saying, oh, there was no hikers there. There was no hikers there. But actually there were, and so we could have people under snow. That's obviously even worse. And those are two of the terms that we'll talk about today. Those ones aren't the ones that confuse me, but or that I find it hard to stick with. Although those ones can have their own challenge. But those are two of the terms we will we'll be dealing with today in terms of evaluating those models, the false positive and the false negative. Let's get right to some of our new terms. Speaking of confusing, confusing matrices? No, confusion matrices are what we're going to be talking about first. So when we talked about just now evaluating our model, just a quick refresher, we talked about categorical data, how we visualize our categorical data. So just a quick refresher on the different types, and we are going to be focusing on that categorical, but continuous is the kind of data that can take any numeric value, sort of any decimal value. So we could always go a little bit bigger or a little bit more precise, right? We might have 1.001. We could always get a little bit more precise with 1.0010001, right? So it's literally continuous. There's no fixed granularity to the concept of this value. So height, weight, range, things like that.
So anything from negative infinity to infinity. That's what you're saying.
Well, certainly in principle, right? I mean,
Yeah.
Obviously, certain column types or height is not good. I'm not going to have a negative height value.
That's true.
But right. I mean, that of course is bound by the domain. But yeah, exactly that in principle the I guess data type of a continuous is continuous in that way as well, kind of boundless. But I think I think of continuous as being kind of continuous within the range. In other words, we can always get more precise, drill in a little bit more. Categorical. Actually, let me jump to ordinal, because ordinal is almost in between, in the sense that ordinal is also ordered, but it is kind of a fixed grain. So it's granular in the sense of maybe being a category that can be ordered like small, medium, and large, right? So where clearly small is in a meaningful way smaller than large. So ordering them, having a number 1, 2, 3 assigned to them is meaningful and useful. Whereas perhaps if we're talking categorical, red, green, and blue, for most purposes, don't have anything that is meaningfully, you can't meaningfully say red is less than blue or more than blue. It's just different. Of course, if we were to get into wavelengths, that might not be true. But most of the time when we're talking about colors, we're just talking about them as kind of vague categories, not their actual radiation wavelength. So
yeah.
So that would be an example of categorical. I mean, the traditional example of apples versus oranges would be another one, right? So apples, preferences aside, apples are neither greater nor less than oranges. They are simply different. And for visualizing our categorical data, and we're going to tap into that one again because that's the one we're most focused on today. One of the early ways we'll use to visualize our categorical data is a histogram. And this just allows us to quickly see the distribution of data. Now, there are a lot of other visualizations that we do with our data, but be it categorical, continuous, ordinal. There are a lot of other visualizations we do. In fact, we talked about a lot of the other ones in other episodes. That said, today, one of the things we're going to talk about is imbalanced data. And looking at our distribution is a really, really important way to identify those imbalances and how those imbalances can then further affect our models down the line. So here, just very quickly looking at this, we see that our true, on the left-hand one, we see that our true category has a lot less instances than our false category. So this is what a histogram can tell us quickly. Here on the right, we have another example: person, animal, tree. Again, we see that we have a lot of instances of animal and person and tree vary slightly, but it's basically just putting those buckets against a count. So that's what we've got. All good, Glenn?
Makes all sense? Good. Yeah, absolutely. We're going to revisit these charts a little bit later when we look at the imbalances too. Yeah,
and the table here too is the same data. It's interesting, right? Because here we do get a a view of it, and I can sort of see, obviously 750 is less than 250, or is less than, it's greater than 250, right? So I know this, but it's not quite as punchy to me, right? It doesn't quite jump out at me, these relationships, and that's one of the reasons why we like to use those histograms, is to get that look to jump out at us, especially if we started having a lot more columns than just 3. Person, animal, tree, it's relatively easy, but it can start to get a lot more challenging. And it really, even same thing here. We are looking at our data and seeing, okay, I've got a lot more false predictions. Now, this actually right off the bat is a little concerning to me to say, well, if my model got 700 false predictions and 300 true, we had one of a couple situations here. One is that I have imbalanced data, and therefore it's doing well, but we are not necessarily training against a balanced data set. So how well is that going to generalize? Or worse, it's just leaning into false too much. All right, so enough of just some basic tables. Let's actually look at what a confusion matrix is.
Which is interesting. It's kind of like the table. It's almost like it was the tables are leading into the data that we're looking
right,
at.
Well, yeah, we're sort of taking those things and sort of like aligning them along a couple different axes here, and then seeing what that gets us. And so that's what we've got right here. Now, if you look at the top, and in this case, we're going to put that ground truth, what we call ground truth. In other words, when we had our training data, in addition to whatever other input columns it had, it also had our known reality, and we're using that so that we can train a model to guess that same label. And our ground truth data tells us that we have this 750 false and 250 true. When we compared that to what our model predicted over here, we can see that we got 700 false predictions and 300 true predictions. So those two things, ignoring the colorful boxes in the middle for a moment, those two things tell us what values we had. So we had in our correct labels, our known correct along the top there, 750 and 250, and then we had 700 and 300 from our model prediction. Now, that alone doesn't tell us how they combine. So this could mean that we had 700 in common, 750 and 700. Maybe all of these 700 came from the 750 actual. We don't know. We don't know what the kind of overlap of those is based just on this data and this data. So the confusion matrix is us actually filling out that information. So here, this first thing that we're going to look at is what we'll call a true negative. And this tells me that actually there was only 500 worth of overlap. So even though this had 750 and this had 700, only 500 of them were in common. So the other 200 that this guessed is false, it guessed incorrectly. And the other 250 that should have been guessed false were not. So we know that we didn't do outstandingly, at least. Now, this is called true negative. The reason I said early on that even this could be a little confusing is, and this is weird, notice how when we start talking about binary data, typically we talk about true and false. But right now, I'm talking about false. And in the terminology of being a true negative, I'm saying that it is an actual negative. It is a predicted negative. So it's the negative and false that are aligning here. The true part. The true part is actually is misleading because we're not talking about the trues at all right now. So what I really mean here is an actual negative or an actual false.
Yeah. So it's the number of correctly labeled false values.
Exactly.
That's what I hear it as.
Exactly. It's the correctly labeled, correctly predicted false values, and of course false and negative are approximately synonymous. So that's what we're talking about here. When I say true, negative, I'm actually talking about the negatives, and the true part simply means actual or correctly guessed. So that brings us to false negatives, or things that I guessed, or my model guessed were negative or guessed were false, but in actuality they were not. So that's why they're false negatives, or incorrectly guessed negatives.
Kind of hints at the next one though, doesn't it?
It does, doesn't it?
Yeah.
What then would be a false positive? Where are we going here?
Glenn, so that's
go
where,
ahead.
Yeah. So that's where the model predicted true, but it was actually in fact false. So that was the other problem, really.
Yeah, 100% correct. So notice that when we use the term false here in this kind of vernacular, in this jargon, what we mean is kind of bad, or incorrect, if you will, right? So incorrect is what we're talking about, and you'll notice the color coding that we have here. What does it do, Glenn? What's the color coding telling us on this screen?
Well, I mean, it's the color coding, but for me, it's actually also the angle. There's almost a diagonal straight line down the middle. So those are the correct answers. Anything else that is not on that diagonal line that's shown in green is incorrect. The ones in the middle are correct. The ones on the outskirts are the ones that are not correct. And I'm not sure if I've answered your question or I've gone somewhere else, Jason. But
you partially answered it. I think you're actually starting to picture when we have that bigger table, because I think probably the folks out there right now are thinking, well, there's only 4. I don't know what you mean by the outskirts.
Yeah, that's true.
But you're definitely correct, because once we start to look at that bigger table, it's only that line right here this way that will actually remain green. So we'll only have, where it was false and I wanted false, it was true and I wanted true, it was, we're hinting at that things to come, it was this third category and I wanted this third category. So yeah, that line right that way starts to become that line of goodness, that line of happiness, the green line there. So yeah, but also we are color coding that to hint. And we've got one section left. Glenn, what is it?
Well, it's the true positive. That's where the model predicted true, and the results were in fact true as well. So these are good answers to have in the model, I guess. So
it's good to know what our model's doing, right? It's important, because we can start to look at what's happening here, right? See that what our model is thinking. So for one thing, we do see that we had this 750 records come in with false value, and 250 come in with a true value. Now already that's clearly what we would call imbalanced. We see the predictions that we made, the 500 that were accurate, and the 50 here that were accurate. But while this we clearly did better with the false, we also did not great and did terrible with the true, right? The true is just really, really off here. So our numbers here and here that we missed, not good, right? So we know that with true, we're not doing a good job. We predicted way off, and only got 50 true positives. So we know that we've got a problem, and we can actually eyeball it pretty quick and see that what happened is my model was able to start cheating towards false a little bit. Oh, actually, no, it didn't cheat towards false a little bit. Never mind, because this was 700. We only guessed 700, and there were actually 750. So in this case, it didn't cheat towards the bigger category. But that is actually often what we'll see. In fact, we will see that in some later categories.
But just going back to our scenario for a second, like if we look at that, if the model predicted true, like for example, there were hikers, but there wasn't actually hikers as well, you'd be able to see that if you're using a cost function to say whether it predicted it or not, you'd just get a number, right? You wouldn't be able to see those particular type of errors that are really important.
Yeah, I mean, yeah, if we're just using like an accuracy metric, a simple accuracy metric, then yeah, it's just going to tell us that basically the percentage that we got 100%. on the nose, which is good information, and it's part of the whole picture. But again, to the point you made about not wasting resources or leaving people on the mountain.
Yeah.
Exactly. We are better informed when we know which direction those mistakes are going in. In addition to the binary confusion matrix, we can use the same pattern with many more categories. And this is where that kind of outskirts concept, I think, comes in. You can see as we build out categories, all of the various combinations of what it really was versus what it guessed are some version of wrong, right? So the outskirts are always going to be wrong, whether it was an animal and I guessed a person, or it was an animal I guessed a tree, it's wrong. Whether it was a tree and I guessed a person or animal, again, it's wrong is wrong. So only person, animal, tree. Only along those diagonals are we in our happy path. And when we look at a matrix like this one, there's not really a easy, crystal clear way to use any kind of negative. So to say that this a or I should say any kind of false, right? See, even I got the term backwards there. Is this a false negative or a false positive? Well, it really depends on the perspective. If you're looking at persons, it's a false positive because I falsely predicted this was a person, right? All of these 200, I falsely predicted it was a person, so it was a false positive from the perspective of a person. From the perspective of animals, it was a false negative because it's actually an animal, but I didn't predict it to be an animal, right? So this is all the animals, and so we know that the things here, these 200 are animals, along with the other 200 in these. So all 400 of these items are animals, but 200 of them were predicted to be a person. Those are false negatives from the perspective of animals. From the perspective of what did I predict? I predicted a person. So if I'm looking at persons, this was a false negative. It was something that should have been, a false positive. See, these things get hard. So this is a false positive from the prediction of person. Now I'm hoping that I said it right the other times. Glenn, did I?
Well, I mean, the way I look at this is that I don't tend to use the false negative, false positive terminology when I've got like a classification like this. Like I think for binary classifications, it's really easy to state the false negative, false positive, etc.
That's probably the safest approach.
Yeah, so I'll just go like it was predicted that so there would be $300 as animal, but we had 200 as a person, and you can just say what was expected and what was actual.
Yeah, let's stay with that safe approach. That's a better idea.
Yeah.
Speaking of our approaches, we're now moving into a demo, which is one of my most favorite approaches for teaching.
Cool. And we get to use the lovely Jupyter notebooks again as well. So if you haven't activated your sandbox, or maybe you're just doing the exercises after, just feel free to just watch and then do it after.
Yeah, why don't you hang out with us? Hang out with us in here for today, and we'll drive the sandbox, and then you can come and visit our module after class, execute this, and then you can be not distracted by our talking while you play with our code and change our code. But when you activate that sandbox, you get that free execution environment. So you just hit these play buttons and this code runs. And today, like many of our other classes, we are downloading our graphing pie library. Just makes things real easy for us to display our visualization functions on screen. And we've got our data CSV here that we're also grabbing from, again, our repository right here, and then just showing you a little bit about it. So here today we have a size. So these are basically objects that were seen by our camera is the idea. Is that right, Glenn?
Yeah, it is. So we've got things like the size of the object. I'm not sure what the roughness represents. I think it's kind of the accuracy of what it thinks it is, what color the object is, how fast it's moving, and what it's predicting it to be. So in
Well,
this
that's
case,
actually, these are the ground truth labels here, right? So
oh,
these are
they
the
are too.
ground truth. So that's not the prediction, yeah. And again, that wouldn't be the predicted confidence either. So I think roughness, yeah. I'm not sure if that refers to like a texture or a quality of the picture, to be honest with you. But and then we got the predominant color of the object here, right?
Yeah.
And whether it's moving, cool.
Yeah. So and then the labels that it's flagged as within the table, and that we'll use for the model generation.
Yeah, and so
training. Yeah.
Yeah, and so presumably to get our training data, maybe we flew those drones around for a couple months without having a machine learning model. We just flew those drones around and had just a bunch of people sit in a room and start labeling those pictures so that we could get the ground truth just based on what people think those images are. So that's one approach. There are many more approaches to getting good labeled data. That is certainly a brute force one, but it's also a common one.
Cool.
So let's see what we've got with our data here. Now
so we've got a few different categories. Sorry, I was going to say we've got a few different categories there: animal, hiker, rock, and tree. And I imagine if you're in a forest, there'd be lots more trees and rocks than hikers and animals.
That's fair. We might, yeah. Maybe our drones were intelligent enough not to take a picture of every tree. Let's give the drones a little credit or something.
Yeah.
But yes, either way, we do have an imbalanced data set. If we were trying to categorize animals or hikers, and hint, we're going to later be trying to categorize hikers based on the scenario that we already shared, we might be in trouble based on this distribution. So we can see that really quickly that this isn't ideal necessarily for what we're trying to do. And now we are looking at the color distribution, and my favorite graph because our graphing library actually picks the colors that will display in our histogram. However, we are displaying colors. So gray is orange, and orange is blue, or cyan, I guess. And red is this pinkish color. Blue is actually red. It's completely silly, but it makes me laugh.
This would be easier if we showed the chart in black and white, I think.
Stop messing with people's brains. It's like one of those what are those kind of reaction time quizzes where they'll put a word on screen, and the word is blue, but it's written in a red font, and then you have to like select either what it says or what the color is.
Yeah.
And see how fast your reaction time is. I don't really know what those are for, but they're fun little things to play on the internet. I don't know what they're supposed to test.
But in particular, that chart's really showing the color of the items as well. So things like trees would be brown or green, rocks would be like a gray or black, maybe depending on the type of rock.
Yeah,
so
we can draw some kind of assumptions there and kind of correlate that too with our assumptions about the labels and what we've got. Yeah, great. And then here we're just looking, we have the size. This one is a continuous feature. So we're using a box plot, which is a choice. We could still use a histogram if we wanted to take continuous values and put them into buckets like 1 through 10. So even if it was 5.2933, it's 1 through 10. So it'd be in a bucket of the 1 through 10 bar. But also using the box and whisker plot is another nice approach a lot of times for continuous data. In this case, maybe not, because the entire box and whiskers are all crushed in the 0 to 70 range because almost all of our data is in there. And then we've got these crazy outliers. I don't think that one's a hiker, but
I'd imagine it's probably a really, really large tree.
Or a mountain categorized as a rock.
Yeah.
All right. And our roughness, which we're not sure what it is, but but it's got a nice normal distribution.
Yeah, it's not too bad.
And motion. Is it moving, and how much? And we can see the answer is not much moving.
And you'd expect that the animals and the hikers are the ones that are moving the most.
Less so than the trees.
Well, the trees would sway depending on the
I
wind.
suppose, yeah, fair enough.
Yeah.
I was trying to be funny, but but very, very good. They would. I think yeah, that's actually probably a good point. That might be why we're clustered down here. I guess that would warrant a little bit more data analysis. One of the things I was thinking when looking at this that we obviously haven't done the data analysis on, but is that maybe hikers and most animals have a relatively slow gait, whereas you have a few outlier animals and birds that can just book it, and so that's what we've got in the long tail here. But it's an interesting point too. We've got a lot of tree data, so you're making me wonder about my assumption there. We've got an awful lot of tree records, so that swaying of trees might also be a factor if we were to dive into the data on that. All right, let's get into building a model.
Awesome.
So first, we're splitting our data. You can see we've got about 1,500 records, our 5 columns, 1,500 records or so in our training, and 600, just over 600 in our test set. And we are using the random forest classifier. If you were with us last week, you learned about that. But you'll also notice that we only have estimators equal 1. So what this really comes down to is we're using a binary tree, or a decision tree, a single decision tree here to do our classification. And we're including the size, roughness, and motion as the features. And our model's trained, so now we want to start to find out how well trained it is. Remember, we know right off the bat that we don't have a balanced data set, but that doesn't necessarily mean we're in trouble, especially depending on what we're trying to accomplish. So let's start measuring the accuracy of it and start also considering those metrics in light of what we want to accomplish. All right. All right, so our accuracy is 8924, and this is along our entire test set. It's not terrible. It correctly predicted 589 of the 660 labels. So, of course, like any metric, it's in context. So when I say not terrible, what does that even mean? It depends. But it's not great, but it's not terrible. But what we have to bear in mind now is even though we used a test set and that was separate from our training set, so we didn't test on the same data set as we trained on, that's good, but we did take it from the same distribution. And if that distribution, for one thing, isn't representative of our real world distribution, or for two, just isn't big enough for us to catch the nuance of all the different categories, then we could still be in trouble. And so that distribution in our case might not be big enough to learn a lot of details about hikers, which are the things that we're most concerned with. And right now, the accuracy anyway doesn't even really tell us what the accuracy doesn't tell us what direction. I think you made this case earlier, Glenn, about that simple measure, that simple metric, not telling us what kind of wrong, right?
Exactly, and that's what we're seeing here. That 589 out of 660.
Like, are we guessing too many hikers, too little hikers, things that have nothing to do with hikers whatsoever because it's confusing trees and rocks? We have no idea.
Yeah. Could we update the model? I mean, we didn't include color in that feature list initially.
That's
so like
true.
if you added other aspects, would the model improve? But you have a baseline of accuracy at the very least. But accuracy is not telling you what type of error. We'll look at that in the last exercise though.
All right. Let's see. So now we're going to see that confusion matrix. And we can tell that we're doing not bad. We know that for our imbalanced data set. We can see that the things are bigger. But let's actually take a prettier look at this. I want to take a nicer, prettier look.
It's really, we'd have to assume that we know what the columns and rows represent as well.
Yeah,
so
yeah, exactly.
In that particular table.
Yeah, that's why we're going to take that prettier look. Thank you for pointing that out. Right? We know that we want the diagonal to be good, to be the biggest numbers, but beyond that, to go to that next level, we definitely are going to want to start to at least have a data dictionary of these columns.
Right.
So what we're doing is once again we're using one of our graphics libraries, and there's quite a bit of kind of boilerplate code here that's not super interesting in terms of turning that output into this pretty heat mapped confusion matrix, but this gives us our labels. And it's also giving us that color coding of basically number or count of matches in the record. And again, while the numbers here are definitely the biggest, once we look at it in this light, in this color coding, we see that we have a problem up in this top left. And that once again corresponds with those smaller data sets that we are smaller sample sets that we had for animal and hiker. And there seems to be a lot of confusion and just not a lot of correct answers up here. A lot of animals confused for hikers and hikers confused for animals. So it's going in both directions. There's just no clarity there.
Yeah, if you look at the rocks and the trees, they're reasonably good predictions, but they're probably not important to our model because we don't want to save rocks and trees. We want to save hikers. And the hikers are not being predicted accurately.
That's right. So we know that we have a problem for our given situation. This isn't going to work well. If we did care about trees, great. In this case, we care that trees are not hikers. All right, so we looked at how our imbalanced data sets, at least we started to take that look at how our imbalanced data sets can drastically affect the quality of the model we're going to output. And we also took a nice look at how accuracy wasn't a good measure of our problem for all things. In particular, the problem that we have and the data set that we have. Accuracy did not do a great job of representing what we cared about. So the confusion matrix helped on that a lot. There are some other metrics and some other things we can do to push that even further. But first, let's drill a little bit more into the situation with data imbalances. Shall we, Glenn?
Let's do it.
So this looks very much, not exactly, there's slightly different counts, but this looks very much like what we were just talking about in our exercise. We've got the same type of distribution where not enough persons, not enough animals, or hikers, we actually have it labeled in our data set, and a lot of trees and rocks. We did start to see where this could go wrong, but let's get a little bit more crisp about it. It wasn't just that we had enough trees and enough rocks. It goes a little further. There's a few different things that can happen with the imbalance. One, we can get our models to just start cheating. Our models want to minimize a loss function, and the loss function is closely related to that accuracy number, right? And in so doing, if you have just a tremendous number of trees and rocks, the model can actually start to just overemphasize trees and rocks. Just guess tree and rock every time. You can imagine if you have a data set that's 95% trees, then I can get to 95% accuracy just by guessing tree all the time. 95% looks like a good number in isolation, but in context, it's not at all good. All I'm doing is hard coding guess tree. That's not useful.
Yeah, the Learn module has another great example from that, Jason, as well, where it talks about the fact that you might be looking for cancer cells and you might be testing 10,000, but there's only one cancer cell. And but that's not detected because the model has emphasized that, yeah, it's all not cancer.
Right. So it guesses not cancer just across the board. It's just hard coded that and gives you 99.999% accuracy. And you didn't actually create a useful model at all.
Yeah.
So perfect. Thank you very much. Yeah, that's an even better example. I love that because that's a real world example versus my tree example. The other thing that can happen too is if you don't have enough, even if you manage to account for that, if you don't have enough examples of the smaller category, the category that's less represented, the model can simply fail to train the complexity and nuance that's necessary to to identify it in identify that category in less common situations. So if there are situations where it's just on the edge of being that category or not, that nuance will be lost. You need a lot of data to capture more nuance, and especially if when we're dealing with things like random forests, they're pretty good at finding nuance. And if we're not giving them enough data to find it, then we're losing out, and we're not going to find the complexity, a sufficiently complex function to account for it. So let's look at a couple of these confusion matrices, that word. It's one of those hard to pluralize ones. So looking at these ones, we've got balanced data, but we've got wrong data in this case. So this is not at all unbalanced data or at all biased data, right? So the model is not biased. It's guessing at exactly the right distribution. And the inputs are 500 and 500 each. So they're well balanced. So the only thing that we're emphasizing in this spot right here is just to say bias is not the same as wrong, and unbalanced is not the same as wrong. So this is perfectly balanced and perfectly unbiased and still only 50% accurate. So it's wrong. The wrongness is different than bias. Here we do have unbalanced data. So if I look at this example, I have 800 total false examples in my ground truth, in my reality data set. So I have 800 and only 200 true. Now, that is very imbalanced. The other thing that we notice here, though, is that my prediction did 500 for each. Now, that's interesting. I actually should have had a nice knowledge check right here, because this would be a perfect opportunity to say, so what do you think? Is that model biased or not? So I'll just ask everyone to think about it for themselves. Maybe we can put some answers in the chat window if we want, but it's something. Is that model biased or not? It has 500 each. And the answer is going to be it actually is a biased model. Now, we don't usually talk about bias in terms of well, I've got the right number, or I've got a balanced amount of predictions against an imbalanced data set. But it is truly an example of bias, because bias is when we are leaning in, when our model is leaning in to one of the categories, when it wants that category to be guessed more often than the data justifies. And in this case, since we have 800 to 200 on our actual data, guessing 500 and 500 is way too much leaning into it. That tells us for some reason, something about it trained it to lean way too far in that one direction of too many truths. Right? Too many truths. So there's something going on there. Now, ideally, we just have balanced data and solve that problem. We have yet another example here, and this one has 500 and 500 reals. Here we have a more classic example of a biased model, because the input data is balanced. However, the model prediction is clearly leaning into false. So despite a balanced 500 and 500 from our inputs, from our training data, our model prediction is way off. So this is a more classic example of what we call bias, where it's the model prediction that's taking things off in a imbalanced direction, and also incorrectly. But we can definitely talk about bias as just being leaning incorrectly too far, or preferring a given answer more than it should. I think we already covered this well enough that the terms are not equivalent, right? The goal, of course, is to be both balanced, unbiased, and accurate. I said both, and then I gave three things, but balanced, unbiased, and accurate are all the goals. but they are not necessarily the same thing. When it comes to bias, we want to make sure that we're fairly representing our data. When it comes to our data balance, that's about the input data and is it sufficiently tilting the scales or not tilting the scales, I suppose, in reality.
Yeah, it's interesting looking at it. Oh.
Yeah, go ahead.
No, it's just interesting. Like when you're talking about the bias before, it looks like when you see examples of bias, there's a large amount of scores in an entire row or an entire column going across. Those tend to be the bias examples. And
I think that's a nice point. Yeah. Especially if you're looking at the actual label part, right? We're seeing that can help represent the imbalance. And when we see that kind of across a horizontal, at least with these ones on our slides, it's actually twisted. It's rotated on our exercises. So you'll all want to notice that that these are rotated. Our actual labels are actually on this axis in our exercises. So be aware of that. But to Glenn's point, yeah, if we see that there's a cluster along either of those lines, rather than along the diagonal, we immediately can be flagged into that either bias or imbalance in the input data, one or the other. And of course, better input data is always an answer. Whenever we talk about problems, more data, more good data is always a solution. So in this case, that could mean getting more instances. Glenn, the office light turn off?
Yeah, just a little bit.
It's funny. It didn't actually make you darker. It just kind of changed the saturation. Your camera had adapted nicely. But in this case, when we say grab more data, we're talking about grabbing more of the examples that are underrepresented in our data set, right? And if you can't do that, actually, sometimes it actually makes sense to subsample your data and just use less of the overrepresented data sets. For instance, with our hiker, it might make sense to not have, you might not want to have a 99-to-1 ratio of hikers to non-hikers. That might actually cause more problem than having less overall data with the hikers having a greater representation if hiker is your sole focus. All right, it's time for a demo. It's time for some water too. All this talking.
This is where we're going to look at the biases and the classification models. Essentially look at the concepts that we've just been talking about.
Absolutely. So yes, resolving biases in our classification models. So we're going to look at some more of these biased examples. In fact, the same bias example, but we'll start to look at playing with our data set in ways to both exacerbate the problem and also look at solving it. All right, let's go get our data again. And we have our graphing and our snow objects again. We've also got a different set of snow objects here. This time we have one called balanced, and you'll see why we have that. You maybe even be able to start guessing why we have it, but don't get ahead of me. We're once again just spitting out what is actually in that data set there. And once again, just taking a look at that distribution. We're not going to go through all of the distributions again, but this one's important again. So we're once again saying, our heavy sampling of trees, rocks, and less so of hiker, and even less so of animal. So we're going to create a new column here called isHiker. And the isHiker is simply going to be a Boolean, where if this column, the one that's tree, rock, hiker, or animal, if that one equals hiker, then the isHiker equals true. And as you might imagine, the vast majority are false because everything that was a tree, a rock, etc. is false. Those things that were hiker is true. So this is exactly what we'd expect. And now we are going to run our training again. So you can see we're doing our split, doing our random forest classifier with our single estimator. So in other words, just a decision tree. And same features, do the fit, and tell us what our train and test accuracies are. And so we've got 95% for our train accuracy, 90-ish% for our test accuracy. Now, I think this is actually a little bit better. We're only focused on is hiker or not is hiker. So it's got a less complicated thing to do. It's our function and therefore our loss function have stopped concerning themselves with whether or not something is a tree or is a rock. They are only concerned with it's not a hiker. So it's a simpler function. So it's actually a little disappointing that it didn't get more better, because I think we had like 89% before, and we're getting 90% now. So very slightly better. And now we are going to look at that confusion matrix again. So very similar code to the code that I didn't want to bother showing last time, and I don't want to bother showing this time. Just some graphing code. It's really all about labels and color codes and axes sizes and boring stuff like that. And this does not look good, to be honest with you. Like even with a 90% precision or accuracy, I should say. We're going to learn about the definition of precision in a little while. With a 90% accuracy, it started to sound not so bad, but when I look at this, it feels not great. I see just the 29 that were actually true but guessed as false, and the 33 that were actually false but we guessed as true, right? So we've got a false positive here, a false negative here, and again, notice that the confusion matrix is rotated from the way we present it on the slides. Both are normal and acceptable ways as long as you pay attention to the labels.
Yeah.
But yeah, this definitely feels like something we should be improving if we were allocating rescue resources based on this model.
But that's an interesting point, though, when you look at the model, and it's really about its applicability. So you might have that accuracy diagonal down the middle, but you want to make sure that your model is more predicted for the outcomes you want. Here we want to predict more hikers being detected. So
right. We'd rather false positives. We'd rather this flag saying that might be a hiker, and we can then show the video or picture or whatever it is to a human who can make that next level judgment call.
Right. So if you have two comparable models, but you're getting the right kind of error, or a less of the error that you don't want, then that's probably a better model.
Absolutely. All right. So now we've grabbed our other data set here. So this is called balanced. Now, if we take a look, we can see that now we've got this data set that is the same number of animals, the same number of hikers, the same number of rocks and trees. However, let's also bear in mind that what we've done is actually refined our concept of the model that we're training. And at this point, we're looking to identify just is hiker or isn't it. And this is a better model to train. This is actually much more on point to our business problem, right? Which is identifying hikers. So it's a much better framing of the problem. We've refined that concept for ourselves, and that's a good thing. But now, this is still not really a balanced data set then, because once I build my is hiker column, I'm still going to end up with an imbalance. Now that might be okay. We still have, now we have more data. It's more imbalanced. Things don't have to be perfectly balanced. But for the sake of demonstration, we're actually going to use a sampling, and we're going to get ourselves a perfect balance. So I'm going to take the number of hikers that we have, and I'm going to use that as the number of samples I'm going to take out of the non-hikers list. So you can see I'm creating that non-hikers data set just from the length of the hikers data set, and then sample basically means grab that many of them, but randomly. So that's the non-hikers, then I combine the hikers and the non-hikers data set right there. And so we can see that now we have equal counts, which is a happy thing. At least for the purposes of this demo, it's a happy thing. So we have the same number of true and false. Now, what we're not doing here, and this would be a great take-home exercise, because we've already got the we've already got the code for training the random forest classifier. That's just up ahead. We just did that right with the imbalanced data. We trained that random forest classifier. What we're not going to do is retrain it with the balanced data, but that's a great take-home exercise to do, to play with this code. Just copy and paste it. You can just create a new code block right here, copy, paste it, input the balanced data set. See how you can improve your metrics. So we're not going to do that, but instead what we're going to do is, because we trained on that imbalanced data set, we want to see how it is going to perform against the balanced data set. In other words, we want to see if the bias in our data, the imbalance in our data led to a bias in the model. So now when we take that balanced data set, how do we do? And the answer is pretty poorly.
Yeah.
Pretty poorly. So
by 15%.
When we have what's that?
Oh, by 15% in that particular case.
Yeah. So what that says is that we're definitely still biasing towards that non-hiker. When we have an equivalent balance, it doesn't do as good a job. So it's still cheating a little bit. It's either cheating or just not as good at recognizing the nuance of the hiker datas. And we can see that as a confusion matrix as well. And once again, the confusion matrix, just like the accuracy in this case, shows that we've got problems. And in fact, now we can see that the problems are much more towards a false negative. So here my predicted label says false, but the actual label is true. So you can see it was leaning. That model was biased towards not a hiker, because we trained it on a data set that had so many more not a hikers. And so it learned to cheat in that direction, and to recognize or failed to learn to recognize the nuance of a hiker. And now we are going to retrain our model, not with the balanced data set like I suggested, because I do want that to be kind of a take-home exercise. I think that's a fun one. That you can, again, just create that code block and actually create something new for yourselves out of this exercise without it just being running our code blocks. Instead, what we're going to do is we're going to ask our library, scikit-learn in this case. So we're going to ask that library's random forest classifier to account for the imbalance in the data. And so we just tell it that we want to use a class weighting. And there are some other algorithms, but basically this says, basically pretend that they're balanced. And we're still going to input the imbalanced data, but we're inputting it into this model that's going to provide different weightings. So it's going to basically give more emphasis to those hiker records, because those are the ones that are underrepresented. So when that loss function, when that training loop recognizes a loss, it's going to make a bigger adjustment for hiker records because they're underrepresented than it would for the other records. So obviously this isn't as good as having more data, but at least it does a reasonable job of, it's still not even a reasonable job relative to having more data. It's not even close, to be honest, but it's better than not accounting for the lack of balance. It's better than not accounting at all. That's really the best thing to say. And so here against the original data set, and so this is again the original training set that is imbalanced. It modified it or improved it ever so slightly, about 1% on each of those metrics, I think. More interesting is to say, okay, take that weighted model, that model that was trained on imbalanced data, but with that weighting to it, and let's see how it does against the balanced data. About a little bit more than 4% improvement is better than just the 1%. Still not amazing, but we can see that it still clearly made a difference. Now, what would probably make an even bigger difference is training it on balanced data, and of course, training it on enough balanced data. And let's take a look at that confusion matrix for that 79% one. It kind of looks the same. this number is a little bit better. That's what we can see there. And it says about the same thing in our here. We had our 4% improvement.
Which is still an improvement. We're always trying to chisel away those additional percents.
That's about what it is, right? Chiseling it away.
Yeah.
Excellent. All right. I'm going to come back to our slide deck here. And now we're going to talk about why, if we like these happy metrics so much, why aren't we using them all the time? Why aren't we using them in our training loop? Why do we have this log loss function and these other things that we're using as loss functions if they're not the metrics that we care about anyway? Why not optimize towards false positives or optimize towards false negatives or whatever it is we decide is the most important thing? And the answer comes down to math. That's the short version of the answer, is just it's math. The longer version is, if you recall, when we talked about cost functions way back in like episode 2 or something, we've touched on it again since, but we talk about cost functions. We mentioned that when we are looking at that cost, so we basically assign parameter values to the things in our model, but those start out random essentially. So these parameters of our model start out as essentially random values. And we need to know whether to get bigger or smaller in order to make a better or worse model. And we can do that if we have a loss function that basically is continuous. Actually, remember we talked about continuous when we talked about our input data. Well, if our loss function is kind of the same thing, right? It's continuous. In other words, if I move a little bit in one way, it gets a little bit worse or a little bit better. It gets a little bit higher or a little bit lower, like this curve that you see on the screen. So if that's the case, I have a curve like this, then I can have my parameter move over, and I can know what the slope of this function is, that loss function is, meaning if I change the value of the parameter, which is what our training does, it changes the values of these model parameters, I can know that the slope for that parameter basically goes down in this direction. So if I go this way along the slope, I am moving in the right direction. Now you can have complex functions you might have some misleading directionality by following the slope, but it eventually works its way out. It eventually does find its way out most of the time, almost all of the time. So we need that kind of continuous function. When it comes to accuracy, basically, especially with categorical accuracy, you are saying, or even ordinal, you're saying that your guess is red or blue. You're saying that your guess is apple or orange. Now, if we move the slider enough, eventually we can trigger that slider, or we can trigger that function to guess apple. And that we can imagine as the step function right here. When we switch our categorical guess, then yes, we are going to have higher accuracy. But accuracy only changes when you change the actual guess. If you move your weight just a little bit, right? If I move my parameter value just a little bit here, just a tiny bit, it doesn't change my guess. It doesn't change what category my model is predicting. If I don't change what category my model is predicting, my accuracy doesn't go up or down. It stays the same. So that's why I can't use accuracy in a lot of other functions, is because I need, as a loss function, something that changes no matter how small the change to my parameter, because I'm going to make tiny, tiny, tiny changes to all of the parameters of my machine learning model. That's what the training loop is doing. It's making tiny, 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 tiny changes. And it can't have the metrics that we care about just stay the same. So if we make a tiny change on this continuous function, it still has a slope, it still moves in the right direction, and eventually we get to where we need to be, which is at a low level of loss. Now, of course, that makes it a heuristic, meaning not the actual metric we care about. It makes it a proxy for the actual metric we care about. Our loss function, in this case log loss, is a proxy for what we care about, which may be accuracy or false positives or precision, as we'll learn about in a little while. But it's a good one it's a good proxy that allows our training function to actually function. And that's basically what we're saying here. It allows our training function to actually function. So it's a good thing that we can find a decent proxy, even if it's not the exact thing that we ultimately care about. On to another demo, sir.
Yeah, I think it's time. It's our last one for today, where we look at the multiple metrics and some of the terminology that's a little bit confusing. I find some of the terminology more confusing than the confusion matrix.
Yeah, this is the part where I have the same thing. This is the section where I mentioned earlier there are things that make me go, I have a hard time memorizing that, and we're there. We're to it. We're to that part. All right, so we're going to once again grab our data sets. We're doing that right now. And then we're going to once again, so it's just the snapshot there. We're going to once again create our isHiker label, do our train test split, create our binary tree, and train our model. Model is trained. All right, this is same one we've been training this whole time. I think this one is not the weighted one.
No, I don't believe so either.
Not the weighted one. Okay, yeah.
No.
And we'll see that then by having the same confusion matrix we had before, right? Yep, so not the weighted matrix. So yep, this is the non-weighted model right here. So this is the confusion matrix that this one with these exact values we've actually seen on all 3 exercises so far.
Yeah, but the next step is where we actually just list out the values that are happening. So what are the true positives, true negatives, false positive, false negatives as well. And we get an assessment really of those classifications.
Yeah, and those are exactly the same numbers as we have in that matrix, right? These are just listed out and most importantly for us, put into variables, because we're going to use those variables here in a minute. Now we've got all sorts of crazy fun metrics. Accuracy, sensitivity, recall. All right, let's just get into them. I'm not going to list them out. Let's just start. They're all ratios, though, of our true positive, true negative, false positive, and false negative. So all the things that are in the confusion matrix. It turns out that depending on your goals, depending on what you're trying to accomplish, different ratios of these can be the most important metric for you, or one of the very important metrics for you. In fact, there's one called F1 score that takes account in essentially all of them and gives you just kind of spits out just a single number. And that's a fairly popular metric too, to just do a kind of a one-shot glance at the quality. We don't actually have the F1 score here, but it's similar in being just a basic calculation of the ratios of the other numbers.
So we're just doing a binary classification here, though, right? We're not doing the animal tree rock kind of situation. It's just true or false for simplicity. Yeah.
Exactly. Yep. So the first one is accuracy. Accuracy is the number of correct predictions divided by all of the predictions. In other words, it's just how many you got right out of everything. So out of everything that you did, how many you got right. This is the one we've been using all along, and we get that, right? So when we say true positive and true negative over number of samples, what we really mean is number you got correct. And that's why these things start to get a little bit hard to track, is because when I say it true positive plus true negative, then I have to kind of remember for myself, oh yeah, that means just everything that I was correct about. So that's what that means. Everything I was correct about, true and true. I was correct.
That diagonal line down the middle, the diagonal line divided by all the totals. Yep.
Where did are you running? There we go. All right, so we can get our accuracy number, which we've seen before. Now, sensitivity and recall. All right, so sensitivity, I've actually mostly seen this referred to as recall, but this is our true positive and false negative. That is our denominator here. So this again
I think I see a problem though. If we have a look at it, if you scroll up a little bit, the model accuracy is actually it's displaying it as a as a float, not as a percentage. So that percentage sign at the end is actually not accurate.
You are correct, sir. Yes, it should be
Yeah.
91%, or it should be 0.91, but it shouldn't be 0.91%. One or the other. Pick, right? Yes, you're right.
Or we can just delete that. It's Jupyter Notebooks. We can delete that percentage.
Yeah, either one. Delete the percent or delete that. Yep, there we go. Ta-da! All right. And sliding on out. So now true positive plus false negative. Once again, it makes me kind of like twists the brain. What do you mean by taking those numbers? And it just means the actually positive. So the ones that were the ground truth was true. That's what our denominator is. So the ones that I guessed were true, the ones that the model guessed were true, over all of the ones that were actually true. How many of the true ones did I guess correctly? Okay, so that's known as recall or sensitivity. And we can see that one came out as well, same problem right there, right? So we gotta adjust that percentage there. And specificity. So I'm even cheating a little bit here and reading. So the actually negative samples, right? So that means the ones that I guessed were negative and that I falsely guessed or I incorrectly guessed were positive. In other words, all of the negatives over the, so how many did I correctly guess right? It's literally the inverse of the previous one. So how many did I get right on the negatives out of all of the negatives? And I guess I should run that one too. Again, these are the jargons that I can never remember the exact right names for. So I think if you internalize the fact that there are such metrics, that these sort of ratios are important and can be important, then you'll also know where to go for reference material, either this module or you'll know how to look it up relatively easily because you've internalized that they exist. The memorization of the particular jargon. Good luck to you if you're able to remember it just on this one session, but I know that I have a hard time with locking it in there. All right, and now we're getting into precision. I mean, like specificity and precision. Like, man, that's those words in my mental map of the English language are very close together, but we're using them as very different things here. So yeah, our precision then is going to be out of all of the things I predicted positive. So now the denominator is not the ground truth. It's not the what really was true. Now the denominator is my predictions. So out of all of my predictions that I said, the things I said were positive, how many of them were matching the ground truth? How many of them actually were positive? And then of course the opposite of that is same. You can see same. Oh, is this? Nope, that's not. Hold on, getting ahead of myself here. False positive rate then. The incorrect positive prediction. So this is actually my false positive and my true negative. So this is back to the ground truth being the important thing, being the denominator, I guess, if you will. And that one, my false positive rate, I get. And I have actually stopped fixing the percentages, I guess. But this is the one that's actually, this is actually the inversion of the specificity. So if we see that 0.05 and we go up a couple more, there's that 0.95. Yeah. And notice that that's the true negative and false positive is the denominator. And again, the true negative and false positive is the denominator. So then it's just whether we're looking at that false positive or we're looking at that true negative. So what kind of negative, in other words? Again, I apologize. We're definitely like spitting out glossary definitions here. For these particular items, you kind of have to know that they exist, and you have to understand that these combinations are things that are meaningful and people use. But it's not easy to internalize all the definitions, especially if you're not practiced on using a particular one on a regular basis.
Yeah, but certainly having that recall is helpful, like you said, and actually knowing, oh, the specificity, it means something to do with this, and you can look it up and go back to it as well.
Yeah, exactly. We have a question here. Why not always select class weight equals balanced? Why is it even a hyperparameter? I mean, the truth is, we're going to make as options just about anything that's going to affect our training. And because again, we're not always necessarily worried about the underrepresented class. If I was training a model that cared more about trees and rocks, I actually probably wouldn't want to use that weight, because it is going to it's going to affect things. And so I'm going to be happier letting my imbalanced data be maybe a little bit biased towards trees and rocks, but be very good at categorizing those if those are the things I care about. And so yeah, I think the other thing to remember is machine learning libraries at this kind of at least stage of the evolution of the discipline, they're still essentially low level. So while they're helping you with a lot of things, there's almost always a window. They're almost always leaky abstractions, these machine learning libraries at this point. So they're getting more and more helpful at doing a lot of the heavy lifting for us and doing some amazing things for us. But there's almost always windows and hatches to go through to hit the fine level tweaks, and that's good. We need those. We're not yet to the point where the libraries and some of the auto functions are just always doing the right thing.
Cool, great question.
Yeah, fantastic. Thank you. Getting back to these slides where.
Well, we're actually up to the knowledge check. So time to ask some questions, Jason. I think you've done lots of the talking. I'll go through these for you today. Let's pop up the first one. And feel free to head over to aka.ms/learntv and give your answers in the chat, and we can certainly see the answers as they're coming through as well.
Yeah, we'd love to see what y'all out there think of these questions too. So please put those if you're up on our Learn TV interface.
Cool.
Put the answers in that chat.
Awesome. So we'll see how confused you are by the confusion matrix. It'd be nice. All right. Question 1. Well, what does it mean to have an imbalanced data set? Is it A, the number of samples is much smaller or greater than is required? Or B, the feature columns may contain missing values? Or C, there's many more training examples that correspond to some outputs or categories than others?
Yeah, so is it the number of samples is smaller or greater than is required? So no, because that's going to be kind of just universal. That's your rows, I guess, is the number of samples. So in general, I guess more is better is the way we tend to look at that, right? That's a generalization, but that's how we look at it. The feature columns contain many missing values. Well, no, that can be a problem, but it's not directly related to imbalance. So how about there are many more training examples that correspond to some outputs, categories, labels, than to some of the other outputs. And that is, of course, the one that I'm selecting. Or maybe not, of course. But that's the one I'm selecting, and it looks like it's correct.
And that's the one that everyone is selecting as well.
Well done, folks.
In the chat, which is super nice.
Always.
All right. Let's move on to question 2. What information can we extract from a single confusion matrix? Is it A, the log loss, or the mean squared error? Is it B, whether the data set has overfit the training set, or C, what kind of mistakes the model's making?
So from our confusion matrix, can we get the log loss and or mean squared error? Well, it's certainly not the purpose of it, so we'll go with no there. Can we get whether the data set has overfit the training set? Not really. I mean, we could certainly start to infer some things along that direction, but that's again not exactly the purpose, and it's not going to tell us truly whether there's a direct overfit if we're just looking at one without looking at, say, the test sets or other real world data sets and their performance. So how about, can it tell us what kind of mistakes the model is making? Sort of, yeah. I mean, at least directionally, right? So of course, what kind is very vague, but yeah, it can tell us directionally what kind of mistakes it's making. Too many trues, too many falses, too many hikers, too many trees. Yep, for sure.
Cool. So the answer there is C. I think everyone that's watching today is just absorbing it all amazingly well, because
Rock
everyone got
on.
that one right as well.
Fabulous.
I think we've got one more question.
We
Is that
do.
right? Yeah. All right. Question 3, why don't we use measures like true positives or accuracy to train our models directly? Today, there are mathematical barriers that prevent these from being used for some training algorithms. B, subtle model improvements often do not affect these metrics. Or C, both of the above.
All right.
Interesting.
Why aren't we using, say, accuracy or true positive? Is it because there are mathematical barriers that prevent these from being used for some training algorithms? There are, right? We talked about kind of the stepwise function and the lack of of ability to kind of gradually move our parameters in the right direction. So yeah, A is good. We know that there's a both of the above option, so I'm gonna keep going, even though I know I like A. Subtle model improvements often do not affect these metrics. That actually is a kind of also refers to that stepwise function being an issue. So if I get things just a little bit more in the right direction for my parameter, it might actually change which category. And if it doesn't change which category, it doesn't change true positive, it doesn't change accuracy, and therefore our training loop would kind of be stuck. It didn't know if it made a good move in that direction or not. So yeah, both of the above seems to be the right way to go.
Cool. I think the answers are still coming in for question 3. But everyone who's answered so far,
so good though. Yeah.
yeah, it's
Well
got
done.
C as well. Yeah, again, so it's perfect score for today for the quizzes.
Is that our first? Might be our first.
I think it might be our first. Absolutely. But that's our look at the content for today. Jason, if you want to summarize it for us.
Yeah, so we looked at some more of our metrics around classification models. In particular, we looked at confusion matrices, and how they can help us get a little bit more insight into our model performance than just either the loss or the simple accuracy number. And then we even looked at how we can take some of those values, the false positive, the true positive, false negative, etc., pull those out and turn those into some additional metrics that some people care about, or I shouldn't say some people care about, but rather some of us will care about for some problem sets. So that was today, our penultimate episode. As you've mentioned, we have one more left.
Yeah. Measuring and optimizing model performance with ROC and ORC. So that's going to be an interesting one.
It's the receiver operating curve. I know we should usually define our acronyms, but man, these ones are really long. So receiver operating curve, which really doesn't even have, or I'm sorry, receiver operating characteristics, which doesn't even have a good real world meaning behind it anymore. Maybe we'll talk about it next week.
We will.
And the area under the curve is what those stand for. So
yeah, we'll certainly be looking at charts and make that all a little bit clearer. Now, we only have a little bit of time for questions. We may actually not have much time at all. And looking at the clock, we probably don't, unfortunately. But we do want to mention that the reason we're a day ahead is because of the Ignite conference as well. So make sure, if you haven't registered for Ignite, tomorrow for a few days, it's an amazing conference, a lot of great sessions. There's some Learn Live sessions in the conference as well by a lot of product managers, speakers, and an amazing group of people.
There may be one on Wednesday by someone that you're seeing right now. If you care, seriously, if you care about architecture in the cloud, and you should, because you are probably developing cloud applications, then please hang out with me and David Blink Edelman to talk about the well-architected framework and the well-architected assessment on Wednesday.
Awesome. Cool. There was just a comment there before that they think their model is leaning towards C in the knowledge checks. That's really great. But
imbalanced data there on the knowledge check.
Yeah. But if you want to go back and follow through the exercises, if you're just watching us to follow along later, aka.ms/learnml-confusion matrix will get you there. And I think that's probably it for today's session. So thanks to everyone for coming, and we'll see you next time.
Thanks a lot.